got it done, but I struggled with like you have to like find like the unique set of characters and then you have to like insert that into like an array or something. But it's okay. I had just had problems like dealing with arrays and
No, I
stuff.
was just wondering
I had to use like
what feature of Python gives the advantage. I
like
just
lists.
linked
No,
lists,
like lists. So I just like
lists.
insert stuff without having to like um
Dot insert or something, yeah, like just like an array sort of list. I forgot.
yeah, like
Do we
lists
have
is
it?
like an array, but like you get to change it and like manipulate it rather than like arrays it's
But how will you? We need to build a heap.
oh no I meant for like it's just like in the beginning before like you start the
But
algorithm.
then for the heap, does Python have a heap like data structure?
It does, but it's okay. I mean, I already did most of it in C++.
That's fine. I mean, if you're comfortable, if it's not too much, if you're already done in Python, then
I already did C++.
oh, okay, okay. All right. So yes, so that one is harder, and please start work on it. April 23. Next week is your midterm. So today, tonight, tomorrow, just in a couple of days, I'll be posting the study guide, and then we'll discuss it, on Tuesday. And there is also one Zybooks assignment, but that's due next week, April 16. Again, don't leave it for the last time because you have your midterm on the weekend. So,
That's it.
all right. So we have been working on dynamic programming, before the break, and we have gone over two major problems. One was the matrix chain multiplication problem. The other one was how we can actually solve the 0 1 knapsack by the using dynamic programming. The thing about these two problems is, yes, they're very like famous. They are sort of like representative problems that we use to learn dynamic programming, but nevertheless, they are still both of them complicated in the sense, because if you're just learning dynamic programming as a beginner, then it might perhaps your very logical first question is going to be, how do I even arrive at such a such an algorithm, right? It makes sense when we understand it because it's already written. But what if we are presented with a problem and we are supposed to write a dynamic programming solution? How will it occur to us to write such an algorithm? So if you recall, we first have to identify whether the problem at hand has the features that will let a dynamic programming solution be applied. So not everything can be solved by um, divide and conquer. Similarly, not everything can be solved by dynamic programming. For something to be solved with dynamic programming, you need to that problem needs to have these three properties. So first of all, when you try to look at a problem, you should see that you have some sub problems that you can break down your problem into, just like the divide and conquer. And the optimal nature of the sub problem is that even though we are looking at the optimal solution for the whole global problem, we need to know that when you have divided your bigger problem into sub problems, then those sub problems also have optimal solutions. It's not like, let's say we are looking for the maximum of something overall, but in the sub problem sometimes you take minimum or you take something intermediate value. That the parity has to be maintained at every level. Maximum global, so maximum at every level, and hence you found the maximum globally. That kind of nature the problem should have. Then very important thing is the overlap of the subproblems. In merge sort and things like that, we clearly divided our list, into half, approximately one half here and one half here. The numbers that you had divided like this, there were actually no intersection, or because those subsets now were disjoint, you separate sets you divided into, right? But things like Fibonacci, if you recall, like if I have to calculate f of 5, f of 5 is dependent on, comes from the sum of the previous f of 4 and f of 3. But f of 4 comes from f of 3, and then f of 2, right? So here we see the overlap. You are using the f of 3 over here, that is required for f of 5, but you're also using the f of 3 over here, that's required in f of 4. That's the overlap. These are sub problems nevertheless, because you split, like you're building up from those smaller problems. But you can see that they are repeated over here. But in the merge sort of scenarios, there's no, the idea is repeated, the logic is repeated, but the data set itself is not repeated. You just split it into half and half, and then further half and half, and so on. So if we are able to recognize this, and Fibonacci is like sort of very representative of why and how dynamic programming can be applied. And then we saw two more cases like that, the matrix chain, as well as the how we can solve 0-1 knapsack with it. Now let's look at more problems, because we want to be sort of like building up to the point where we, given a problem, we can start from scratch and develop our own dynamic programming solutions. So this is a problem here called coin row problem. First, let's read about it and then see what it is asking us to do. So what do we have here? In this case, in this example, we only have like 6 coins, but we could have any number n of coins, right? We have 6 over here. So those C1, C2, Cn are the denominations or the value of each coin. Doesn't matter, whether it's like a legitimate currency system or not. It's just an example. So you can see that these have 6 coins are valued 5, 1, 2, and so on. Now, they don't have to be distinct either. They can be repeated. As we can see, 2 and 2 are there. And what is the goal of the problem? Is to pick up the maximum amount of money. So the optimal solution in this case is to get the max value you can. Optimal can sometimes be minimum, sometimes can be maximum, doesn't matter. Depends on the problem. So here we want to find the maximum amount of money we can collect if we are picking up the coins in such a manner that we're not picking up any adjacent coins. So if you pick up 5, you cannot pick up 1, but then you can pick up 2, or if you did not pick up 2, I mean, it doesn't have to be alternate. You can directly pick up 10 after that. As long as the next coin you pick up is not adjacent to the one you just picked up. So if you pick up 10 after 5, then you are not allowed to pick up 6. What? No, I mean, can you pick them repetitively? No, there's only one of each there. So this one gives us 17. It's not necessary you even pick up the first one. So, but you don't know, if you just, once you moved forward, you cannot go back, right? So like once you reach 1, you cannot say, okay, I'm going to, 5 was bigger, so I'm going to pick that. You just have to make a selection, keep moving forward. So what do you think? How to approach? So this is, let's say we also know that there is a dynamic programming solution possible to this. But okay, from scratch, like, do you think there's a dynamic programming solution possible to this? What property of this problem makes it so? What is it about this problem that divide and conquer does not work, but dynamic may work? What? It's iterative. Okay, then did you mean sub-problem wise? Can it be divided into sub-problems? So, I mean, we are looking at 6 coin problem here, right? The sub-problem property, what did it say? That if we are looking for the optimal sum for 6 coins like that, if there were just 5 coins to arrive whatever we could with the maximum with this one, would it still give us lead up to the maximum overall? I mean, you have not seen 2 yet, but whatever you could have achieved at this point, would that be good for those 5 numbers? Whatever you could have achieved, let's say for 3, if you had only 3 coins, would that be sufficient for those 3 coins? But yes. So that is the optimal nature of the subproblems. You can divide it into subproblems. Those subproblems are optimal. Then how about the subproblem overlap? Is there some kind of dependency from one to the other? Oh, okay, let's not, we can come back to that later, but how will you approach solving this? Like, how will you, before we even write the algorithm, what do you think the solution can be? Or how can we solve this problem? You can actually try to solve this just without any algorithm, like just working with the numbers we have. What do you think the maximum we can get over here? Which numbers are going to give us the maximum? 10 and 2? Right. And it's okay to pick them up because they're not adjacent. So this would have given us 17. Nothing else can give us better. Looks like no other combination exists over here. If you pick up 5, the next options are either you could pick up 2, but then you have to pick up either 6 or 2. So that would give us 13. Then how do we, for solving this, for solving dynamic programming sort of problems, we first have to, because we're looking at the repetitive nature and some kind of overlap, the trick is to look at, develop a recurrence relation, a recursive sort of formula. Because if you recall in Fibonacci, what we did was we did have the dependency in such a manner where Fn was the sum of Fn minus 1 and Fn minus 2, and you had some base cases. Over here, a similar recurrence formula, how can we build? What is going to be, so let's say these are 6 coins, but for given any n coins, the final solution is going to be f of n. Right. In Fibonacci, our f of n was f of n minus 1 plus f of n minus 2. Right? In this case, what do you think? What is the final value of all those n coins? Any idea? So you're saying pick the greatest, but then we do not know which one is the greatest. We can see over here because the numbers are given, but let's say we cannot see that over there. And this could be like a very big n, so we don't know where the maximum number is. And we need to keep the complexity at a minimum. So let's say, for example, if any given n numbers like this, let's say you do search for the maximum, right? But then the second maximum could be somewhere right over here, or then the third maximum could be somewhere right over here, fourth could be here. So we cannot keep searching that because that would incur a lot of time. We can skip The which coin? Which one is that? The 2? Skip that. Fn minus 1. So which means that you're saying that we did not take 2 for some reason because we could not, perhaps, right? Because if 6 was a part of the solution, then 2 cannot be part of the solution, right? So that's a very good start. So the idea here is that for if our previous optimal solution for the n minus 1 coins was f of n minus 1, right? But that included the second last coin over there. For the adjacency rule, we cannot pick 2 then because we already picked 6. For the 5 numbers, 6 was a part of it, so we could not pick 2. Which means that 2 is not part of the solution if then f of n, the optimal with n is just the optimal with n minus 1. Does that make sense? Does that make sense to everyone? So this is just trying to sort of like the top-down approach is just saying that if the nth coin is not a part of the solution, then why was it not a part of the solution? Because perhaps you included 6. That is why you are not able to pick up 2. Because for any positive number, even how small it is, like 1, 2, it will only add to the maximum, right? But the thing is, you're not able to pick up 2 because it's adjacent to 6, right? So perhaps you already picked up 6, given what you picked up earlier, which is why for the 6 coins, for the n coins, you cannot pick up the last coin. So then you would just have to say that the f of n is just the f of n minus 1 because you cannot add the last coin. Yes, so there only seem to be 2 cases. 2 is not a part of the solution, 2 is part of the solution. If 2 is part of the solution, then what is the value of f of n? Then 2 is a part, right? So it's 2 plus something, right? Then is it 2 plus what? And what was that? F of n? F of n includes 2. So now you're breaking up. You cannot do the f of n minus 1 because if you pick up 2, you cannot pick up 6, right? F of n minus 2. Does this make sense to everyone? 5 and 1 were there. 5 and 1 both cannot be there because they're adjacent. Started with which 2? The first 2? Okay. You cannot add 10 because you are here, right? So the only options then you can have either 6 or 2. When you already selected the 2 over here, you intentionally did not take 5 and 1. So the optimal till 2 was, in your case, it was not optimal. It is just one possible solution, right? It's not optimal though, right? Here we are saying that for whatever reason, for an unseen number of coins, let's say we arrived at an optimal. What's the best we could have done if 2 wasn't there? What's the best we could have done? That's the f of n minus 1, right? Whatever the best we could have done. In that case, the best, I don't know, it would be 5 plus 2 plus, it would be 5 plus 2 plus 6, right? I think. But whatever the best you could have done with a problem solution at f of n minus 1 is, considering all of these coins. But then you have the next coin, right? That means that if you do not pick up 2, then your f of n solution is simply made of whatever was already f of n minus 1, right? Because 2 doesn't even matter because you did not take it, right? But if 2 is a part of the solution, then that means your solution actually added 2, right? But the only way you can add 2 is never include 6. And whatever you did before, that was already found out by f of n minus 2, right? So this is the recursive sort of formula. Dynamic is, the underlying idea behind it is going to be recursive. Only we'll not use recursion because we want to get rid of recursion and we want to just use like an iterative solution for this. So this is basically the answer, the whole idea behind this particular problem. But is it starting to then make sense how you can approach these kind of problems? Okay, now that you have a recurrence relation or like a recursive function or something like that, and you eventually don't want to use recursion, and even if you did, right, you need to have base cases, right? What are the base cases for our problem? Base case is like if n is 0, right? If n is 0, then your value, your f of n is 0, right? There's no value if you have no coins. If n is 1, it will just be the first coin. So we'll call it, is equal to c of 1, c1. So for a general case, here we can see the values, like they are written over here. But for a general case, your coins are just going to be C1, C2, Cn, right? So the last coin is the coin that is the Cn value. So instead of the 2, we can just check if Cn is not a part of the solution, then this is the result. Else if Cn is a part, just use that value, whatever that last coin value is. Okay, now the next activity I would like to give you is, let's write the dynamic function for this. Let's write it. Can you write it on paper or computer or wherever? And tell me, what the algorithm looks like? Don't use recursion. What do? We fill up an array, like a matrix. If it's a two-dimensional, like generally in the previous two examples, we are filling up two-dimensional arrays, right? In this case, is a one-dimensional array going to solve the problem? Right? It's just, let's call that array S. So what does the solution look like? And once you arrive at the solution, can you fill up this kind of an array and let us know, what answer, what maximum value are you going to get with this particular problem? But first, when whoever finishes writing the algorithm, let's just then share it with the class so they can actually use that to find out, to fill up this array.
That's right. Oh, that'll. Hello?
Yeah, I can hear.
Oh, can you? It's not.
Yeah.
Oh, no way. Okay, yeah, it's not showing me on my screen that I am. I hope other people might be able to, but yeah, I have a suggestion
sure
of how to
if they
do this
can-
one.
If this is
Okay.
loud enough. Go ahead.
I gave a slightly long-winded text explanation, but basically it's that you do it 3 terms at a time. So you look at the first 3 terms, and the observation I was making was that the only reason you would use the second term in your final answer is if the value of the second term is greater than the value of the first term plus the third term. So if it's not, then your final answer is going to include the first term. Like in that original example, you would keep the 5. Whereas in this second example you've given us, the second term is so large that 4 is greater than the value of 1 plus 1. So you would actually keep the second term. And so the next iteration, basically, if you keep the second term, you throw out all 3 of the first terms and then move on as if those never existed to like the next 3 terms. Whereas in the other case, if you keep the first term, if you keep the 5, then you only throw out the first 2 terms and move on to the next 3 after that. I hope that made some sense.
Will your idea work for the second one that I've drawn over there?
Which one? The 1, 1, and 1?
Yeah, 4 ones.
Yes, because B, the second term doesn't exceed the value of the first plus the third. So you would keep the first term and then move on to the next 3 and end up keeping. Oh, you can't keep that one. You have to. Oh no, you throw out the first 2. The maximum of that is 2, right? Because you can only take 2 of them.
So how are you going to look at 3? Okay, so do you have an algorithm you can actually write? Like how will you sort of like write the iterative algorithm, like from I is equal to 1 to n? Is that so? Okay. What is your?
It's more conceptual than I know that it is. I'm not sure exactly how I'd write it, but that's goal would be.
What's the run time you're thinking?
Let's see, you're comparing. I want to say it's O of n, but I'm probably wrong about that because you're doing. So you're adding the first term and the third term, and comparing that to the second, and you're either throwing away 2 terms at a time or 3 terms at a time. Worst case, you're throwing out 2 terms at a time. Doing one comparison. I think that's O of n. Unless you're about to tell me that O of n is impossible for this. I'm not sure, but I think it's O.
Keep working on the algorithm. So if you arrive at something else, then keep working on that. Then we'll discuss. Okay. So keep building on the idea, Jeffrey, isn't it?
Yeah.
Okay, Jeffrey. So write out an algorithm, and then let's discuss about. So let the other students also think, and let's see if you have something common, or maybe they come up with something different, and then we'll see, okay, which one may be better, or they can actually both work. Let's see. Okay, so write out an algorithm. Like, let's say you were supposed to write a pseudocode for your idea. How would you go about it? So the pseudocode you're thinking is bottom up or top down? You start building from the first of the list, like from 1, 2, 3, or from n down to 1. Okay, let's. How would you like? Let's try to get like a rough pseudocode if what you're thinking about. If you do like an n down to 1, do you think it will be a recursive iteration? So recursive is good also, as long as we are not sort of recomputing the values. Recall that recursive has an extra constant in the RAM. How the compiler deals with it, sorry, the CPU deals with it. It's going to build an array stack because calls. That is like extra memory. So recursion definitely will still give you dynamic solution, but space complexity can be a little higher. And that's fine. Keep trying with the recursive one as well. Once you have that, then you can just switch around from bottom up.
think I've got mine.
Can you have you written it on the computer somewhere? Can you share? Type it out in Word or something so you can share.
Yeah. This is. Oh, sorry. There was a part at the beginning of this. Do it again. Oh, array size is supposed to be array A. Array C is meant to be the final. Like,
Are you sharing your screen?
oh no, I put it in the text chat. Sorry. I hope that. I don't know if that came through.
People will be able to see the text chat.
Let's see if I can.
Not as clearly. I think.
Not 100% sure. This. Maybe it worked. Then I can do this.
Add elements, AI plus 1, AI plus 2 to where? To a new array?
Oh, to B. So B is like your working array as you're going through this. So at the end of the loop, you have to remove all the elements from B. So B resets every. It's like a working array.
Oh.
Does this make kind of sense? I don't know if this is a solution you had in mind, but this is the first
one. Does this mean that you're able to select? I think somebody here in the class also was, I think, was talking about whether they can see those 3 coins ahead, right? You're standing in that queue, the coins are in front of you, and you're looking at you're selectively making that choice, right? What if you don't have that option? You see what I'm saying? Your idea is correct. This is one solution that will work, that can work. But then you're actually selectively making a greedy choice, isn't it?
Yes.
In a way, right?
You are, but I think it's just because in this particular case, I don't think it's actually possible for. It is based on the logic that you would, if you're not going to use the second term, then you must use the first because it would be. I feel like that part is necessitated just by the way we're doing this. So yes, it is a greedy. It's definitely a greedy choice. That's for sure. At every step.
So could you store your load problems, then you can use them later on instead of foreseeing the coins like that? Couldn't you just go with one coin, then the next coin? Because let's say you don't have an option of looking all the coins. You can only see the what you have. And then once you move forward, you cannot go back. Do you see?
Right. But this, I mean, the point of this is to just move forward through the array but starting with the first 3 elements. I mean, can you go one element at a time? Because any given element, you have to kind of know what the value of the next element is to know whether you should include it or not, right?
I mean, it makes sense. Does it make sense to you?
I mean, this approach makes sense to me. But it's, yeah, again, it, like you were saying, it does require knowledge of 3 at a time. But I'm not sure how you could come to an optimal solution without knowing at least 3 elements. Or well, and this needs the edge case of what happens when you have only one element or two elements, like when you get to the end of the array, which means this just needs like one or two more if statements for like if there's only one element, pick that one element, or if there's two elements, just pick the largest of the two. But those are, I think, the only edge cases that this doesn't count for.
So did anyone here come up with any other solution? Does this make sense? Can you think of something different if we don't have to see all those three coins together? So this approach is good, Jeffrey. We just want to see. This is one of the ways we can do it, right? Okay, can you fill up that array that we have? Can you start to build the C array? Eventual C? No, not the C array.
Can you remind me what the values were? I could here. Is that the one?
I just erased them. Just come up with any example of your own and then try to walk through this. Yeah, any example would do.
Like for this, you would like the first iteration would be you look at these first three values, 1, 4, and 1, and you're checking is 4 greater than the first term plus the third term, which it is. So you would pull 4. You then, so like this is array A. Array B is your working array. So you pull 1, 4, and 1 into the working array, and C is your final. So as you look at these three terms, is the second term greater than these two combined? It is. Okay, so then we keep that term and we throw out all three. We get rid of these from A, and we get rid of these from B, and then we start over with these three terms. So let's see, B, oh, sorry, we actually copy them based on the logic I'm using. And this one, once again, it's 17. So we get rid of those three, and we're left with just the 9. We get 9 and end up with that out of whatever I had originally, which was, so what did I just say it was? I think I just said it was 4, 17, and 9 out of that original, which I assume is the correct answer for this. I'm not totally sure.
So the earlier recurrent
So-
solution, why that did you use that one in here?
No, this is just kind of I'm sorry. I know it doesn't involve any recurrence. I just sort of thought through it and came up with this.
Looks like order N, I think. You're moving 3 at a time, a little bit extra steps at every 3.
Yeah, basically. And you're doing, I mean, this comparison takes a few steps, though, like comparing this to these two terms added together. But I mean, that's a constant duplicative.
Idea, okay, this is good. One of the things that I would like to say over here is that how dynamic programming generally works, like as a technique, is start to build your solution from bottom up, meaning for 0, you have 0. For 1, you have C1. What do you have for C? What do you have for the second coin? What do you have for 2 coins? Just generally, I mean, this solution is working, I know, but there's nothing wrong with it. But what I'm thinking is it a dynamic programming solution? Do you think it is? It's a solution, nevertheless. But I'm just thinking, is it a dynamic programming solution?
Yes,
No.
yeah.
In a way, it is, because your sub problems are 3 at a time, and there is some overlap, right?
Yeah. Depending on the results, you may use the results of your first one to determine your second one, because it'll change your next set. Is it is it terms 3, 4, and 5, or terms 4, 5, and 6? That depends on the results of the first operation.
Okay. Okay. All right. This works. This works. And then did anybody come up with something different, or does this make sense to everyone here? Okay, the one that I had in mind uses this one here, but that's great. If you have something else, that also works. You know, you either have the last coin and then your recurrence looks like this, or you don't have the last coin, then your looks like this. But can your f of n be different? I mean, like sometimes if you want to include the last coin or you don't want to include, depending on what you have done before, right?
Did I stop screen sharing? Sorry, taking back.
That's fine. Yeah, okay. Just
I'm not sure if I should. I'm just asking.
Send this algorithm to me later on so I can actually post this for everyone later on as well. They can then see the one that I have, and then maybe both work. Technically, both work. Definitely, they both work. You're just using some extra space. That's fine. You're using 3 arrays, right?
Yes. Or well, it's assuming that the answer is already in, so I'm using 2. Granted, they're I'm creating.
Yeah. The last one you're just using to store the result, right? So that's not technically, you can just keep outputting it, right? I think the C
Right.
array.
Oh yeah, that the C could actually just be a running total. It actually could just be a variable that keeps a sum. I was just putting them into an array to keep it for myself. But yeah, there doesn't need to be an array C. That could just be a variable that just keeps getting plus equals this instead of that.
But here's something that I found a little bit of a snag in your solution. Maybe correct me if I'm wrong. You found the solution for the given n coins, right? What if I take off your 3 and 9 in the end, okay? And now I tell you that what's the solution for the remaining one? Can your current, what do you have?
Right. I was saying it needs 2. That's why I was writing this if size equals 1. There's 2 edge cases that I haven't written, which is if size equals 1 and if size equals 2. If a dot array size, those are the 2 edge cases it needs, which I haven't put in it yet. But then everything else assumes, the size is 3 or greater, then it works. So it just needs a custom thing for if array size is 1, then you do this. A I guess this is just if you do it's just because if there's only 1 left, you would just do that, and if you have 2, you need to figure out which one's the biggest. Else actually you do this way. I think that does it, because the idea is you do if you remove 3 and 9, you do these 3. Then when you're stuck with the last 2, it's just you choose the biggest. So these are just the 2 edge cases. So it would end up in this edge case, and you have the larger one, so you would add the larger one. You both of them. Then the size is 0. The loop ends. I think that does it. I should double check this.
Okay, just send me this later on so then I can actually post this so everyone can see later as well. Okay.
Sure.
Then can I stop sharing your screen so I can share mine then?
Yeah.
Okay, so here is what I had in mind here. That solution does work. And yes, you can have several different solutions. So the one that we are working with is that, you can either include the nth coin, then you would have to not take the n minus 1th coin, or not include the nth coin, then it'll just be f of n minus 1. So at any given time, you will make the best of these two, right? So basically, what you have is the max of this, for the f of n. So the solution that, let's say I keep an array called f, and that's the same size as the number of coins n. And how I fill it up is f of 0. So this is my pseudocode beginning. F of 0 is 0 because there is no coin. Then f of 1, only one coin is C1, right? So I'm using the idea of how we built for the Fibonacci, like how we build that one array that carries the solutions, the sub-solutions. So the iterative would be for the I is equal to 2, I less than equal to n. The f of n, because I'm storing as I'm going further, I'm storing my value, whatever I compute till that point in that array. So this would just be using this particular recurrence relation. So max of either f of I minus 1, because I did not include, if I do not include the ith coin, or I think your solution is pretty much the same. Sort of like it's expanded out a little, but it looks like the same, I think. So I'm using this exact same recurrence relation that we had. And we get the value including the ith coin. Does this make sense? This is the algorithm, but how will it work? So let's say we have coin I, so we have here the 0, 1, 2, 3. What was the original example that we had? Five, 1, 2, 10, 6, 2. These are the 6 coins. What is the value of your f of I, this is the coin. So the 0th coin value is 0. So here, if we are on the first coin, what is the value? Only 5, right? Now you have coin number 1 and 2. Let's say you have 5 and 1. Just use this. What is the value of f of 2? What is f of I minus in f of 2? What is f of I minus 1? C2 plus f of 0, isn't it? When I put the I over there. So what is f of 1? 5. What is coin number 2? It's 1. 1 plus 0. So we are using pretty much the same idea. 2 coins at a time, I think. So this is f of 1 is between 5 and 1. 5 is maximum, right? So the value till this point is 5. Does it make sense? What is the next one then? What? 5 again. So f of 3 is equal to max of f of 2, and then because I minus 1, then C3 plus f of I minus 2, which is 1. So what is f of 2? It's 5. What is coin number 3? Is 2. And what is f of 1? It's 7. Sorry, it's 5. So 2 plus 5 is 7, isn't it? So we'll take the maximum between 7 and 5, and this will then become 7. So we are eventually technically doing the same thing that Jeffrey is doing. At this point, it is telling us that if you had only 5 and 1 coins, if you had only 5 coin, your value is 5. If you had 5 and 1 coins, your value is also 5. If you have 5, 1, and 2, what's the best you can do by picking no adjacent coins, right? The best you can do is 7, right? 5 and 2 is 7, right? So, but pretty much the same thing I would say. So this is 7 here. Then what happens in f of 4? So Jeffrey, are you still there?
Sorry, yes, I am.
So using your idea, suppose these are the coins we have, right? Then for any of these coins, let's say we had only 1, or we have the first 2, or we have the first 3, or the first 4. Are we able to get, using your A or B arrays, those sub-problem values?
In fairness, I didn't need the arrays. I've rewritten it so that there's only the original one, so it's one array and one integer. Basically, yes.
So
mean,
let's
like-
say, yeah. So
Do you want me to talk through this example? Happen or?
the one that you had, I mean, can you, like, let's say, once we run your algorithm, right? So can he then later on retrieve that if we did not have the 6 coins, we only had the 4, what would be the maximum value you could do with the 4?
Based on what you're showing right here?
No, based on your algorithm, not this one.
Right, but I mean based on those coins. That's what I'm saying.
Yeah, these
Based
coins.
on the 5, 1, 2, 10. Okay.
Yes, yes.
Yeah. Yeah, I mean it would be 15. Take the 5 and the 10.
It would be 15.
Yeah.
Yes. Yes. It would be 15. So eventually that 15 is then being used later on, right? You're moving that value further on, right, to be used later? Yes, that is why you arrive at the maximum eventually, right?
Right. I mean, I'm putting it in a variable. I'm not sure what the variable. I guess I could do whatever with it. Yeah, it could be moved on to later.
Right. So in here we have, yes, go on.
I was gonna say I mean, it's just kind of figure just instead of making a final array, it really should just be an integer that's keeping a sum total as it goes along. So if that integer represents the sum total, then you add on an extra number. Potentially, you could just, well, that number could screw up a lot of things if it's like a gigantic number or something. Like you probably have to recalculate every time you add a new one. But yeah, you could just use that, keep going with it.
Why we keep these subproblem values? But hold on, before we move further, does this make sense? This particular algorithm, does it make sense? We actually arrived at the recurrence earlier, right? This one here, and we simply use the same recurrence value over here. So the one that you are saying, I think, Jeffrey, is that, why we need the array. So you're talking about this particular F array. And instead, why, store those intermediate values, because eventually they're just, the 15 is going to be eventually used to make 17. The idea behind that is that, just saying that, you can actually later on replace, I mean, it's maybe a variant of this problem, right? Let's say you actually replace these two coins for some n minus something coins, right? All the lower value subproblems are already done. So you have those already. With the starting 5, 1, 2, 10, the max you could have achieved was 15 by the fourth coin, which is why basically, I think dynamic programming basically does, keep storing the subproblem values to be eventually used later on. May or may not be needed later on, but that's one of the sort of like the ways this technique basically uses. I would say it does actually build and stores those intermediate values. You can say that, yes, it uses some extra space, exactly order n, right? So eventually when you'll keep going, you'll fill up this particular cell, you will fill up this particular cell. Finally, here you will get the value as 17, which is the optimal for this particular example. But does it make sense? Did this make any questions on this one here? The dynamic programming part in this particular problem is, you have subproblems, right? The subproblems means that instead of 6 coins, if you only had 4, you can still arrive at the optimal solution with the 4, which is 15. Let's say we only had these coins. The optimal you could achieve had 15 at this point, right? So the dynamic programming technique is to first sort of like build like a recursive solution for it, a repetitive. So this one was the one that we started off with. Include the last coin, and then you only are able to get the fn minus 2 with it, or do not include the last coin, and then you can only then f of n is equal to f of n minus 1. But you do not know, which one is better, so you will take the maximum because your goal is the maximum value, right? Once you have this recursive function, this is the goal, the idea behind the dynamic solution. You have to find that recurrence. And because there is actually an overlap, because f of n minus 2, f of n minus 1, because you're actually needing them at every stages, instead of recomputing them every time, just like the Fibonacci, because you need f of 4, f of 3, several different places, right? Simply start building from bottom up. That's the dynamic programming approach, that start building from 0, 1, 2, all the way till f of n. So once you've already built the lower values, once you will go to the higher value, you can use any of the lower values because you've already computed them, which is why we use the array, because we save it. Because at this particular point, I would need something here and something here. At this particular point, I would need something here and something here. I already needed it here. I'm needing it again over here. Let me not recompute it. Compute it once, save it, and then use it. That's the whole major idea behind. So first, arrive at a recurrence relation. That is mostly intuitively how you arrive. So we started off with this one over here. Once you arrive over here, coding it actually becomes, coding it was sort of easier with just the recurrence relation. But it needs more practice, yes. It needs a lot more practice. So, get very, very well versed with, any technique at any point. But this one is simple because it just is a little bit like Fibonacci. It's only using like a single dimensional array. Whereas the other ones that we saw, the knapsack, two-dimensional, we have to think, how to gather the subproblems. All right. Okay, so we can wrap up today. And please read the midterm study guide that I'll be posting, because we would like to discuss it definitely on Tuesday. And, you have your midterm